What is time? Time in quantum mechanics enters as an extrinsic and absolute parameter marking the evolution of the system. This can be measured by a laboratory clock and is independent of the dynamics of the system. Yet, time can also be treated as an observable, as illustrated by the events like the decay of a nucleon, tunneling, and or when a particle arrives at some special point, such as the time of arrival. But what exactly is this time of arrival? Hi, my name is Jennie Umipig, and in this thesis, I will be discussing about the momentum quantum time of arrival. In classical mechanics, given a particle prepared in some initial state, we can then ask what is the time it takes for the particle to arrive at point Q, starting for example at the origin. This is the classical time of arrival problem. The quantum time of arrival problem answers the same question, yet instead of a single value of time, it gives us distribution. In momentum space, it answers the question, given a particle with an initial momentum p, what would be the time it takes for the particle to have a final momentum pf, in this case we set to 0. In this thesis, we introduce the momentum time of arrival for the linear potential and harmonic oscillator and investigate the dynamics of the eigenfunctions of the time of arrival operators. So, how do we construct the time of arrival? We do so by quantization, which derives the quantum observable from the classical observable by promoting the position and momentum into operators satisfying the canonical commutation relation. Specifically, we impose the condition that h and t be conjugate with each other. That is, the Poisson bracket of h and t equals 1. We introduce the Hamiltonian Lagrangian and invert this equation to solve for t. In doing so, we can have the following prescription to calculate the momentum time of arrival, so that lastly, we can then quantize it using the Wiles simple symmetric and Born-Jordan quantization. Once we have the time of arrival operators, we can then investigate the dynamics of their eigenfunctions. Thank you.